Look closely at the center of this steel I-beam. It is physically bending downward, reacting to an immense pressure pressing on its span. To calculate exactly how much a beam like that deflects, we have to move beyond writing out formulas by hand. Today, we are translating that theoretical math into a functional, automated script using MATLAB, Octave, or FreeMat. Before we begin, open up your preferred development environment. You will need a basic understanding of array syntax to follow along. By executing this specific code, you'll bypass manual calculations and build a practical engineering tool that solves structural deflection. Step 1 is defining the material properties. In your script, initialize 3 core physical variables: the elastic modulus, the moment of inertia, and the single beam element length. This is a view of your IDE workspace. Run your script immediately to validate your setup. You should see E, I, and L stored safely in memory as numerical values.
With the properties loaded, we can introduce the coding sequence required to build our foundational 4x4 local element stiffness matrix. As you type this out, watch your punctuation. The most common syntax failure here is forgetting to use semicolons to separate your rows, which will break the matrix dimensions. Once typed, execute this block of code without a trailing semicolon at the end. This forces the software to print the generated local matrix directly into your console. This diagram shows exactly how your output should look. Notice the symmetrical pairs of numbers across the main diagonal. If your printed numbers do not mirror each other, you likely have a typo in your brackets. Establishing a flawless local matrix is your critical first milestone. A single incorrect digit here will ripple outward and corrupt the entire simulation. Now we move to the global stiffness matrix. To save system memory, pre-allocate the space for it by setting up a zero matrix framework matched to your total nodes. We will populate those zeros using a standard for loop, which systematically iterates through each localized element and plots its matrix into the larger framework. This grid visualizes the mapping process. When 2 elements share a physical node, their matrices slide in and overlap at the shared coordinate. Instead of overwriting, the loop sums the overlapping numbers at these junctions. Let the loop finish, then check your workspace pane to verify the final row and column dimensions of your newly assembled global matrix. Because we linked those overlapping nodes, this matrix accurately captures the continuous, unbroken physical nature of the entire beam before outside loads are introduced. Right now, that unconstrained matrix represents a beam floating freely. To make it useful, we must apply boundary conditions that act as physical supports, like anchoring one end to a structural wall. We code this by partitioning the matrix. Systematically zero out the specific rows and columns that are tied to the fixed wall node, leaving a 1 on the diagonal. If you fail to lock these supports, the solver will crash and return a singular matrix error. The software cannot calculate displacement for an object that isn't anchored down. With the beam secured, define your applied force vector. Map your specific physical load directly to its corresponding node in the code. Finally, deploy the \/ operator. In linear algebra, this is the most efficient tool to solve the system and find your exact nodal displacements. Applying these rigid boundary constraints provides the necessary physical context, transforming the generic stiffness matrix into a solvable model of a real-world structure. With the solver finished running, instruct the program to print your final calculated displacement vector in the console window. This console output shows the correct baseline values. Compare your calculated vector to these numbers right now to guarantee your script is accurate. Now, let's look at what we've accomplished. Add your final plotting commands to visually graph the original state of the beam against the deflected state. This chart plots the direct result of your code. A straight horizontal line representing our unloaded beam morphs into a curving trajectory mapping the precise physical deflection caused by the weight. You now possess a functioning automated solver. Because your matrices handle a simple point load, you are ready to adapt this code for distributed real-world loads in our next build.